When you look at modern stealth aircraft, you can't help but wonder why the weird and unconventional shapes and geometry. Of course, it's all about stealth and staying invisible, but why does geometry matter so much? What is it about a shape that can make something disappear from radar? Looking at the profile of a P-51 Mustang or an F-16 Falcon or even the F-35, their shapes make intuitive sense. They feature sweeping curves, rounded noses, and smooth transitions. These shapes exist to solve a problem in fluid dynamics. Air has mass and viscosity. When an object moves through it, the air resists. To minimize this resistance, engineers design aircraft to part the air smoothly, allowing it to flow over the fuselage and rejoin at the rear with minimal turbulence. For the first half-century of aviation, the shape of an aircraft was mostly a result of fluid dynamics optimization. Form followed aerodynamic function. But down the line, aircraft began to take on shapes that completely defied established aerodynamics, aircraft that looked almost like alien spacecraft. Aerospace engineers did not build these bizarre aircraft by accident. They built them because something had superseded fluid dynamics. The shape of an aircraft was no longer determined by how it interacted with the air. It was instead determined by how it interacted with the waves, electromagnetic waves specifically. To understand why stealth planes look so incredibly weird, we have to examine some math behind radar detection, the limitations of early computers, and the physical design rules that keep these machines off radar screens. Contrary to some popular beliefs, the goal of stealth is not literal invisibility. An aircraft will always reflect some energy. The goal is to delay detection and reduce the range of enemy tracking systems. To achieve this, engineers target one specific variable in the radar range equation. Received power equals transmitted power multiplied by antenna gain squared, multiplied by wavelength squared, multiplied by the radar cross-section, all divided by 4 pi cubed times the distance to the fourth power. A pilot cannot change the enemy's transmitted power. They cannot change the wavelength. They can only change the radar cross-section, or sigma. This is the measure of how much electromagnetic energy the aircraft intercepts and scatters back toward the receiver. When an electromagnetic wave strikes the conductive metal skin of an aircraft, the oscillating electric field of the wave forces free electrons in the metal to move. These oscillating electrons generate their own electromagnetic field, radiating energy outward. To minimize sigma, the aircraft must direct this radiated field away from the source. A traditional aircraft fuselage is a cylinder. A nose cone is a sphere. A curved surface possesses an infinite number of tangent planes. No matter what angle the radar wave arrives from, there will always be a specific point on that curve where the surface points directly back at the radar transmitter. The electrons at that specific point will re-radiate energy directly back to the source. Building an airplane out of cylinders and spheres guarantees a radar return. Engineers realized this in the late 1950s when designing the SR-71 Blackbird. Before computers could calculate radar cross-sections and simulations, engineers at Lockheed Skunk Works had to use slide rules and intuition. They knew a spherical nose cone was a massive radar reflector. So they flattened it. They created a sharp, continuous blade that runs all the way around the nose and blends into the wings, called a chine. This gave the SR-71 its bizarre cobra-like profile. Instead of hitting a flat wall or a sphere, incoming radar waves hit this sharp aerodynamic blade and were scattered sideways into empty space. But slide rule stealth had its limits. To completely eliminate the radar return, engineers thought of building an aircraft entirely out of flat plates. On a perfectly flat conductive plate, re-radiated energy is highly directional. Because all the electrons on the flat surface oscillate in phase, the angle of reflection equals the angle of incidence. If the flat plate is angled away from the radar receiver, the energy propagates into empty space. The receiver detects nothing. Understanding this was somewhat easy. Designing an entire aircraft out of flat plates required extreme precision, which wasn't as easy.
Calculating the radar cross-section of a complex shape involves solving Maxwell's equations, describing how electric and magnetic fields propagate over conductive surfaces. In the 1970s, calculating continuous electromagnetic scattering over a 3D curved surface was very hard. Computers then lacked the processing power. The solution came from Russian physicist Pyotr Umfimtsev. He published a paper outlining the physical theory of diffraction, providing a mathematical framework for calculating the scattering of electromagnetic waves off the edges of two-dimensional flat objects. Engineers at Lockheed translated this paper and wrote a computer program called Echo-1. It allowed them to input the coordinates of flat two-dimensional facets. The computer calculated the edge currents and the scattering behavior. The result was something that resembles an F-117 Nighthawk. Its bizarre crystal-like shape was a direct physical artifact of 70s processing limits. The aircraft was faceted because flat triangles were the only geometry the computer could easily verify. The underside of the F-117 looks flat, but it isn't. It was made up of carefully oriented flat facets that redirect incident radar energy away from the transmitting radar, rather than reflecting it back, thereby reducing its radar cross-section.
The reliance on flat plates solved the electromagnetic problem, but introduced massive aerodynamic problems. Air prefers gradual pressure gradients. Sharp edges create low-pressure wakes, vortices, and immense drag. The F-117 was aerodynamically unstable in all three axes of flight. It required continuous input from a quadruple redundant fly-by-wire computer system simply to avoid tumbling out of the sky. Specular reflection also comes with a severe vulnerability. If two flat surfaces meet at a 90-degree angle, they form a corner reflector. A corner reflector traps the incoming wave. The wave bounces off the first surface, hits the second surface, and is sent directly back to the transmitter, regardless of the angle of incidence. Standard aircraft designs are full of corner reflectors. The vertical stabilizer meets the horizontal stabilizer at 90 degrees. The wings meet the fuselage at 90 degrees. Stealth design demands the elimination of these intersections. To avoid creating a corner reflector on the F-117, the design team used a heavily swept V-tail configuration. But there is one corner reflector you cannot design away: the pilot. A human pilot wearing a spherical helmet, sitting inside a complex ejection seat surrounded by angular screens, is an absolute nightmare for radar. If a radar wave enters the cockpit, it will bounce around the interior and shoot right back out. Look closely at the glass canopy of an F-22 or an F-35. It isn't clear. It has a strange, metallic, yellowish gold tint. To prevent radar waves from entering the cockpit, the glass is infused with a microscopic layer of indium tin oxide, or actual gold. This conductive coating makes the canopy transparent to visible light, but completely opaque to radar frequencies. To a radar wave, the glass looks like a smooth, solid sheet of metal. External stores ruin stealth. A missile mounted on a wing pylon introduces cylinders, spheres, and intersecting planes. A stealth fighter must store its weapons internally. This affects the volumetric shape of the fuselage. The aircraft must be incredibly thick and bulky to house fuel, landing gear, and ordnance with an internal base. Engines present an even bigger problem. A jet engine is a massive resonant cavity. The compressor at the front is a spinning disk of metallic blades. If an incoming radar wave enters the air intake, it reflects off the compressor face and travels straight back out to the receiver. Engineers block this line of sight using serpentine ducts. The intakes on the F-22 curve inward and upward. The wave bounces between the walls of the duct, which are lined with radar-absorbent material, dissipating the energy before it can exit.
The F-35 utilizes a diverterless supersonic inlet. Traditional fighters use a splitter plate to separate turbulent boundary layer air from the intake, but this creates a radar trapping gap. The F-35 replaces it with a three-dimensional compression bump. Aerodynamically, it forces bad air away from the inlet. Electromagnetically, it acts as a geometric shield, scattering incoming radar waves away from the engine. But the front of the engine is only half the problem. If an enemy radar is pinging the aircraft from behind, the rear turbine blades are just as exposed. This is partly why stealth planes have weird exhausts. The F-117 crushed its exhaust pipes into totally flat horizontal slits, often called the platypus exhaust. This completely hid the spinning turbines from rear-facing radar, while simultaneously flattening out the hot exhaust plume to evade infrared heat-seeking missiles. The F-22 follows a somewhat similar logic, utilizing flat two-dimensional rectangular nozzles to mask its engines from behind.
By the late 1970s, the F-117 proved that flat plates worked, but the aerodynamic issue was too severe. Engineers needed to know if continuous curves could also be of any use against radar detection. Northrop Grumman built a highly classified testbed aircraft called Tacit Blue. It featured a bizarre, blocky, curved fuselage. It was notoriously unstable and was nicknamed the Alien School Bus or the Whale, but it successfully proved that if the math was done correctly, smooth curves could scatter radar just as effectively as sharp facets. As supercomputers grew more powerful in the 1980s, engineers could finally calculate Maxwell's equations over continuous curves. This led to the smooth, flying wing shape of the B-2 Spirit, and eventually the F-22 Raptor.
Modern stealth fighters look less weird than the F-117 because massive computing power allowed them to regain aerodynamic efficiency. But their planforms still follow strict geometric rules. The primary rule is edge alignment. When an electromagnetic wave strikes the leading edge of a wing, diffraction occurs. The wave scatters outward. If an aircraft features wings, tails, and panels at varying angles, it scatters radar waves in multiple directions, creating a continuous radar return. Look at the top-down profile of an F-22 Raptor. The leading edge of the right wing is exactly parallel to the trailing edge of the left wing. The air intakes, the engine nozzles, and even the access panels share these exact angles. By aligning every major edge to these same specific angles, the aircraft only returns a radar signal in a few extremely narrow directions. A scanning radar receiver will register a microsecond spike of energy, which the processing software will immediately filter out as background noise.
While the overall shape relies on aligned edges, the surface of modern stealth aircraft presents another challenge. Radar waves attach to the conductive skin of the plane. These traveling waves, or creeping waves, move along the fuselage until they encounter a discontinuity, a seam between metal panels, the gap around a weapon bay, or the edge of a landing gear door. When the traveling wave hits this gap, it scatters a return signal. To mitigate this, the access hatches on stealth aircraft feature jagged, serrated edges. These zigzag saw teeth are angled to match the primary edge alignment of the wings. Furthermore, engineers modify the surface impedance. The aircraft is coated in radar-absorbent material, or RAM. The seams and gaps are covered in a specialized conductive tape, featuring a precise electrical gradient. It gradually changes the conductivity of the surface as the traveling wave approaches the gap. This causes the wave to be absorbed and dissipated as heat before it can scatter.
Every feature on a stealth aircraft is a calculated engineering compromise. A commercial airliner compromises speed for fuel efficiency. A traditional fighter jet compromises payload capacity for maneuverability. A stealth aircraft compromises aerodynamic purity for electromagnetic survivability. The shapes of these aircraft appear weird and unconventional because they are solving a problem we cannot see.